Hi, I'm Alexander Zamora, and I'm the controls lead here at Cyclone RoboSub. And this is Manny the Manatee. Manny the Manatee has 8 thrusters, an onboard 9-axis IMU with a magnetometer, accelerometer, and gyroscope, as well as a DVL, which also has an IMU on board. We also have 2 cameras and a downward-facing camera for our vision system.
Hi, I'm Kory Haydon, one of the engineers on the controls team for Cyclone RoboSub. I'm going to show you how we use MATLAB and Simulink to design, tune, and validate our robot. Our primary innovation with the introduction of MATLAB to our workflow is our ability to rapidly switch between 3 distinct operational modes: fully simulated, tethered, and untethered. This allows us to reliably and repeatably test the robot controller across a wide variety of test cases, making the transition from simulation to reality seamless. Here's one of our fully simulated models. Let's start in this pink subsystem on the left. This section is the mission manager. The responsibility of the mission manager is to determine what Manny's current objective is and translate that into a waypoint for Manny to drive to. Here we have the low-level controller. This model takes commands from the mission manager and translates it into specific target vectors for the PID controller. The PID controller is by far our most complicated subsystem. It is actually 4 PID controllers arranged in a cascaded fashion to allow finer tuning and more transparency of the control logic. Throughout the PID controller, injector blocks have been added. These blocks let us trick the controller into operating with a fixed state error, which is very useful for tuning. The PWM outputs of the controller is sent to the plant model. The plant simulates thruster forces, drag, buoyancy, hydrodynamic added mass, and gravity, with a 6th degree of freedom dynamic simulation using quaternion kinematics. We started with an analytically determined best guess for the various physical parameters needed for the simulation, like drag coefficients and moments of inertia, then iteratively improved our guesses using pool test data. The simulated controller is only useful if it works on realistic sensor data. For this purpose, we built a sensor model subsystem that simulates the IMU and the DVL, with added sensor noise and drift. We also use an Unreal Engine co-simulation to simulate the camera feeds, which I'll talk more about shortly. The simulated sensor data gets fed into the state estimator and the work-in-progress video processing subsystem, which combines the DVL, IMU, and in the future camera data to estimate Manny's position, attitude, and rates in the pool to enable feedback control.
After validation and simulation, we moved to the tethered control mode. In this mode, we use the Ethernet tether connected to the robot to test it on the workbench or in the pool from a computer running MATLAB. This lets us run hardware in the loop and controller in the loop tests on the real hardware while taking advantage of MATLAB's debugging, tuning, and data visualization features. We can either use the controller in MATLAB while controlling the real robot, or use the controller on the robot while controlling a simulated robot.
This functionality is enabled by MATLAB's Robot Operating System, or ROS toolbox. We use ROS to send PWM commands to the software team's code that runs the robot's Raspberry Pi. This is one of the Simulink models we use for the tethered mode. The structure is similar to the fully simulated model. However, the connections to the dynamic sim and the sensors have been replaced with ROS blocks connected to the real robot. We also added the remote control with a video game controller in tethered mode. We use this mode primarily for pool testing to drive the robot back to the starting point between autonomous runs, but we can also use it for research deployments and to gather computer vision training data. So our controller has passed all of our tests in simulation, and it's passed all of our tests while tethered. We need to take all our MATLAB code for the controller and sensor fusion and translate it into C++ to run on the onboard Raspberry Pi. For this, we use Simulink Coder to automatically generate ROS2 nodes from our Simulink model. So far, we've successfully validated and run with a reduced scope using dead reckoning for navigation. We accomplished our goal of creating a system to deploy, validate, and test our controllers in real time with the help of the ROS toolbox within Simulink. Our stretch goal for this year's competition is the completion of the computer vision subsystem. This is the Unreal Engine simulation we have constructed. Here, we have models of the pool and various tasks, as well as more accurate lighting, caustics, shadows, and underwater image distortion. We can set Manny's position, attitude, and rates using Simulink blocks from the Simulink 3D animation toolbox and the Unreal Engine with Simulink interface plugin. We built this simulation before we realized an Unreal project file was being provided to us by MathWorks for the competition, which proved an excellent learning experience for our team members. We are currently developing systems to do edge finding, object detection, and range and bearing stereo vision measurements using MATLAB's computer vision toolbox with simulated data from Unreal Engine. Thanks for watching, and I hope you are rooting for Manny in this year's RoboSub competition.